Chairman. Good morning, everyone. My name is Afsal, and today I'm going to talk about graphene electric field sensor for lightning detection. So I'm from Japan Advanced Institute of Science and Technology, which is roughly 3 hours north from here. And this project is done in collaboration with Otowa Electric, which is a lightning arrestor manufacturing company, which is actually very near from here. The place is Amagasaki. Probably you might have seen the railway station when you travel here. So why we wanted to have a lightning sensor? So in Japan particularly, this is very important because lightning is very highly frequent natural disaster here. So as per government policy and also as a business perspective, having a lightning sensor is very important. In addition, we are much more interested because we are based here and we have more winter lightning strikes than other parts of the Japan. So this slide summarizes the broad idea for the company in particular. So what they would like to do is to have sensors installed across Japan, collect data, and to have a predicting system. We are not just focusing on detecting lightning, but to have a system where we can predict lightning, say 30 minutes before the lightning strikes. This is very important for people like who play golf or children who play in the playground because they cannot take shelter immediately, right? So if there is some warning system, they can take shelter inside a building or something. Also, maybe a bit futuristic, but we would like to have a sensor which can be installed on watch or something, so we get notification much more easily. Now, why can't we do that now? So the current sensor, which is used by the company also generally is field mill, which is very accurate, but the problem is it is huge in size and it uses large power. Also, it is a bit expensive. So the company approached us asking whether we can do something in a much smaller scale. So we are a group which works on 2D materials, mainly graphene. So we thought, why can't we try graphene? And most of you might have familiar with graphene. So our device looks very simple. So this is a silicon dioxide substrate. We put graphene on top and just make 2 contacts to apply voltage, measure current, or apply current, measure voltage. So the actual device looks something like this. Graphene is here. Now, before testing our device outside for lightning, we wanted to see how the device responds for electric field. So here is a setup we made, which mimics which creates some electric field, kind of mimic the atmospheric electric field. So we apply some voltage to the top plate, and so there is an electric field in between the top and bottom plate, and the sensor is put at the center. Now, how do we, and we put the device in a chip carrier so as to avoid having any probes which will interfere with the electric field. Now, how do we make the measurement? Again, very easy. We apply a source drain voltage, measure the current. Also, the field is turned on. And while the current is being measured, we suddenly turn off the field and see if there is any change in the source drain current. Here is the response of the sensor. 2 things important here. One, the sensor responds differently to positive and negative electric field. You can see for positive electric field, it is increasing after the field is turned off, and for negative electric field, it is decreasing. Another important thing, the difference between drain current when the field is on and off is increasing with the magnitude of the electric field. So the sensor can detect both the polarity as well as the magnitude of the electric field, which is nice. So we based the sensitivity of the sensor on this aspect. That is, the larger the difference in drain current when the field is on and off, the larger the sensitivity. So the sensitivity is defined as the rate of change of drain current. Now, the sensor works well at higher electric field, but when the electric field is smaller, for example, 333 volt per meter, the difference between drain current is much smaller. So we wanted to see whether we can improve this difference. So we look for ways where we can improve. Now, here is a slide which explains how the sensor works. I'm not going to the detail of the theory. A simple cartoon we made for our university festival for the non-scientific audience. So what happens is, here is a graphene, the SiO2, and there are defect states on the interface of graphene and the SiO2. So when electric field is applied because of the Coulomb interaction, some of the electrons gets transferred into the traps in huge numbers. So this transfer of electrons changes the carrier density and changes the drain current. So this is the simple working mechanism. So we wanted to see how we can improve. So if you are someone who is familiar with graphene, one of the common method used to make high quality graphene devices is to encapsulate graphene between HBN. So HBN is another two-dimensional material, insulator. So the surface of silicon, although it looks very flat and smooth, is atomically very rough. So we use the HBN, which is another atomically flat material, makes or allows graphene to sit on a very flat surface without any defects or something. Also, the top HBN protects graphene from unwanted doping because we do a lot of lithography and use a lot of chemicals. So with this method, the graphene is very clean. And you can see that when we calculate the mobility is 4 times higher for encapsulated graphene. And the difference in drain current when the field is on and off is also improved. So as the sensitivity is almost double. But again, we encountered a slight issue. We could not again go to smaller electric field because now the charges has to pass through the HBN to reach the traps. So, which was again an issue. So we again thought what we can do further. So another thing we thought is, okay, the carriers are moving. We found that if we increase the speed of the carriers moving, there are more chances of charges trapping. But another aspect is, if there are more charges available at a particular energy level, then again, there is a probability of more charges getting trapped. So in physics terms, we have to find a material which has higher density of states than graphene. And one material, a 2D material, which has higher density of states than graphene is MOS2. MOS2 is a semiconductor, so it has less mobility than graphene, but has very high density of states. So again, we tried, again, a simple device. So just MOS2 on silicon dioxide. And again, we could see it responds to the the electric field. But the good part is it has much more sensitivity than graphene or encapsulated graphene. One issue which I have not highlighted here is the source drain current for MOS2 is much lower than graphene, since MOS2 is a semiconductor and mobility is less. So that is something we have to work on in the future. Now, all these measurements or experiments are done inside the laboratory. But our actual aim is to do some detect the lightning or atmospheric electric field. So we took our graphene device for field test. So here is the usual field mill, which the company or the people generally use. And inside this small box, we have our graphene device. And we connected graphene device on a solar panel. So we don't use any external power supply. It acts like a standalone unit. Now, this graph shows actual event of atmospheric electric field variation. This is lightning data, which we collect from Japan Meteorological Agency. It is called lightning detection network. The dots represent lightning events. So the x-axis is the time, and the y-axis is the distance at which the lightning happened from our field test site. Now, the peaks here are the lightning discharge from the clouds. You can see that one important thing here, when we compare it to the industry standard field mill, our graphene sensor almost replicates the results, which is fantastic. And if we look at the lightning events, almost all of them are captured by graphene. But there are two peaks which we can see in both graphene and in the field mill, but it is not appearing in the LiDAR data. So one possibility could be that the lightning event happened at a far distance. But if we look at the peaks are very sharp and high intense, which means, so the intensity implies that the lightning happened at a near site, near to the field test site. So it seems that the LiDAR did not detect the lightning event, but the field mill and graphene sensor could detect the lightning event. Now, another thing I would like you to notice is, for example, this is especially evident in the field mill data. The response becomes negative in this area. So this means that there is some negative electric field. And if you see the schematic of the cloud, the bottom of the cloud always have negative charges, because when the ice molecules inside the cloud collide with each other, the heavy ones get negative charge and they move to the bottom. So this overall shift in that broad peaks or the negative part represents the movement of the cloud. So again, to confirm, we again took data from JMA, Japan Material Agency. Now this time we took the rainfall intensity data, which shows the cloud movement. And here is the data from 7:30 to 8:10. And so 7:30 to 8, you can see there are clouds. So the yellow and red color represents clouds. Here is the field test site. And these cross and circle shows the lightning event. And you can see that when after 8, the clouds have passed and the baseline goes to 0, which means we could detect both lightning events and also the cloud movement, which shows the variation in atmospheric electric field intensity. And now we have installed our sensor in different parts of Japan. And some of them are in extreme conditions. For example, we installed one on top of Mount Fuji to see how the sensor works in extreme cold condition. And another one in, it is blackened, but it is an island which is famous for extreme thunderstorms. So we want to see how the sensor works in different extreme conditions. Yeah, that's all. Thank you so much.